In the second part of the Simulink tutorial, I will show how you can evaluate the performance of a proportional integral controller, which is shown here in the bottom left. So the voltage is now going to be defined as a linear combination of the error. The error is the difference between a reference velocity and the actual velocity, and then the second term has the integral of that same error. I have already implemented it in the window using the previous blocks that I had assembled in part 1. This is because actually all of these blocks are the same as those that I used in part 1, so I just needed another integrator, 2 gains and 2 summations. So this can be done using the same techniques as were used in part 1. In here are the proportional and integral gains. So this is the term that goes to the integral. So this is the integral value. And if you want, you can change this label to Ki to reflect the definition of the controller, and this to Kp. So you just click on the text level, and you can, using text techniques, you can change the name of these variables. I have the gain here in front of the integrator. This can go either way. You could put your gain before or after and get the same results. So if I run now this simulation, I have the same warning message as I had before, and again I can plot the variable, and this gives me the plot which is here. And you see that now we have a response which is a little bit slower than the one that we had before. Of course, it is determined by the poles of the closed-loop system here, which are different from the poles of the open-loop system. The value that we reach is 10. That's because I didn't change the value of the step here. It is still 10, which before was 10 volts. Now it's 10 radians per second, and so we converge to 10 radians per second. So as you see, you can quickly add a compensator of some form to the model as we had developed in the first part and evaluate its performance. Now I'd like to show a way to plot the results without going back to the MATLAB command windows. This can be done by clicking on a signal here. So I do a right click, and then I get some options here, and I'm gonna click here on Create and Connect Viewer Simulink Scope. This creates a scope window, which I'm gonna bring here, and this is the window in which we will plot the speed. Now what I will also do is look at the voltage, which is here, and so I need a second, either a second window or a second sub-window in the scope window, which is what I'm going to show here. So I'm going to right-click on this signal, which is the voltage. But first of all, I'm going to go to the Signal and Scope Manager, and that's a useful window sometimes to have to see what kind of scopes you have. This one shows here the scope with one signal. I'm going to add a second one, and you see that immediately becomes a window with 2 sub-windows. We'll increase the size a little bit and take this out of the way. And now I still need to go back to the signal and now go to connect to the viewer. It's an existing viewer, not a new one. So I go to Scope, Axis 2, and this will run the simulation to this will run the voltage to the second sub-window. If I click on Play or Run, if you prefer, it runs the simulation. And now you don't have to go to the workspace, it plots it immediately, but it doesn't automatically auto-scale it. You have to go into this box here, click on it, and you see that it scales it. And we have the same velocity response as before, but we also have the voltage, which is only 1 volt, because it takes only 1 volt to get to 10 radians per second. So this is convenient to change simulations and see the results in real time if you like, so that you can move a little quicker. Now I'd like to show a function which I like to use in Simulink and is useful for quite a few different purposes. but in particular in this context I like it to produce some arbitrary reference signals, so you could test the response of the system to various combination of steps or sinusoids, but especially quickly changing the parameters of these signals. So I'm going to delete this part here and go back to the browser here and go to user-defined function and pull out the MATLAB functions. So what this will allow me to do is to insert in the diagram here a function which is an M file similar to the M files that you can use to program in MATLAB. Then in the commonly used blocks, or maybe in the sources, I will get a clock. Right, the clock gives the time in the simulation. Gonna move things a little bit so I have more space. Alright, we have this. Now I should advise you that in some implementation of MATLAB, and Simulink in particular, you need to install a compiler to be able to insert the MATLAB function, and this may require a separate installation. The MATLAB help files have some information on that, and there are some free compilers that you can install. So it's not too hard, and I think it's worth the trouble. So I'm going to connect these signals, and then this function here is going to define the new reference input. So I'm going to go here, and the output is going to be what we call omega ref, and the input is time. And here we can write any functions of time that we want. So I'm going to first write omega ref is equal to 0, and then I'm going to say if the time is greater than 0.1, omega ref is equal to 0.2, and then if the time is greater than 0.3, omega ref is equal to 200. And here I meant to say 100. So that's going to say now 100 radians per second and 200 radians per second at time 0.1 and 0.3 respectively. So you see now I've just created a combination of two steps, and I could have done it by putting two-step functions, but this method allows me to create a variety of other functions without having to worry about finding the blocks. So I'm going to close this, and I need now to do the simulation a little longer, so I'm going to do 0.5, and I'm going to run it again. So first it's compiling all this code, and then it's going to run the simulation, which is pretty quick. Alright, again I have to rescale, and you now see that I have two steps at 100 and 200 radians per second, or 10 volts and 20 volts respectively. So the controller is able to achieve tracking of the reference command with some delay, of course, but the real system has a delay as well. So this is a pretty good damped response. So we could of course change this reference as we wish now to have different profiles, and we can immediately see the results in the scope. Note that we can also save the axis. This will allow us to not have to rescale as long as the signals still fit in the same window. When we're done with this, we can go back and again save our model. So I'm going to do an MDL model. I already have the DCM model. This one I'm going to save it as DCMPI so that I can reuse it later.